Hello, and welcome to the Circuits unit in Phys 1201. In this lecture, we're going to first look at how we represent circuits, and then we're going to look at Kirchhoff's laws, which we use for analyzing them, and a few consequences of Kirchhoff's laws. We need to be able to draw circuits if we're going to talk about them, and we want to be able to draw them pretty quickly. So we're going to use schematic diagrams. So the first symbol we need is for a wire, and it's just a line. And that doesn't necessarily represent a real physical wire. It's just any good conductor that connects two pieces of the circuit together. Where wires branch at a junction, you just have lines meeting. A battery is represented this way, and there's a lot of variation in how people represent batteries, but this is a pretty typical one. And by convention, the large line, the long line on the top here, is the positive terminal of the battery, and the short line is the negative terminal. A resistor is a zigzag line like this. A capacitor looks like two parallel plates. Here's a light bulb. We'll occasionally use that. And here's one type of switch. This is a switch that you can open and close. When it's open, then no current can flow through. When it's closed, then current flows through. But another type of switch would be something like this, where it can switch back and forth between making a connection with this wire or with this wire. There's a fair bit of variation in all of these. Sometimes it's regional variation. So for example, the zigzag line is the North American symbol for a resistor. The British one is a box like this. There are different types of capacitors, and for some capacitors it matters which plate is the positive and which is the negative. Capacitors like that are represented this way. And of course, I'm ignoring all sorts of symbols for circuit elements that we won't talk about: diodes, inductors, transistors, all sorts of things. Here's a pretty simple circuit. It has a battery that I'm going to call epsilon, and we'll increasingly use that as a symbol for a battery, a resistor that I'm going to call R, and a capacitor that I'm going to call C. And we would put these labels so that we can now say these are variables. This is the resistance of this resistor, this is the capacitance of this capacitor, this is the voltage across this battery. But now something to realize is that the only thing that matters here is what's connected to what, and there are many ways of drawing it that would leave it unchanged. So for example, if I just swap the capacitor and the resistor, I have made no change to the circuit, because leaving the battery, I arrive at a junction. And in either of these diagrams, I now have a choice between a branch that takes me through the resistor or a branch that takes me through the capacitor. And I then arrive back at another junction, which will then take me back to the battery. And so the connectivity of these two diagrams is the same, and so they're actually representing the same circuit. Similarly, if I just change angles of things, again, I haven't changed the circuit at all. All of the connectivity is the same. And finally, I could take this battery around the corner here, and again, that hasn't changed the circuit. Everything is still connected to everything else the same way. There are two fundamental laws called Kirchhoff's laws, which govern the way circuits operate. And in fact, we've already seen both of them. We just haven't named them. So the first is called Kirchhoff's loop law, and it's a law about voltages. And we've already seen it. You know that if you go in a circle, because potential is only a function of position, you must arrive back at the same potential that you started. And so the sum of the voltages, or changes of potential, that you go through in your path must be zero. This is called Kirchhoff's loop law, and it's sometimes also called Kirchhoff's voltage law. The other is Kirchhoff's junction law. And again, we've already seen this. It's simply a statement of conservation of charge, that if current flows into a junction, the amount of current flowing out must be the same, because you can't have charge building up in the junction, and you also can't destroy or create charge. And if all this seems just slightly abstract, then think in terms of the ski hill analogy. The loop law is just saying that if you start at the bottom of the hill and go up the chairlift, you will have to come back down a distance equal to the distance you came up the chairlift. And so the sum of all the height differences that you go through add up to 0. And similarly, if a bunch of skiers are arriving at the top of the chairlift, then the number of them that go down all the available runs on the hill has to add up to the number who are arriving at the top of the chairlift. We often use the term circuit element, and it just means any piece of a circuit, whether it's a resistor or a battery or a capacitor or whatever. If we don't want to be specific about what it is, we call it a circuit element. Kirchhoff's laws now let us talk about various rules for how circuit elements can be connected that are special cases. So the first one is what's called in series. So here are two resistors, A and B, but I don't want to be specific to resistors. I want to talk about any circuit element. So these could be a battery and a resistor, or two batteries, or a battery and a capacitor, or just anything. So I'm just going to use these two colored boxes to represent two circuit elements. I don't care what they are. And they are in series if, first of all, one end of one of them is connected to one end of the other, as in this case. And second of all, there are no junctions in between. Now, if those conditions are met, we say this is in series. And the reason this is important is if you think about currents. Any charge that enters A must proceed through it, leave it, and go on to pass through B. And so that tells you that all the current that flows through A must flow through B. The currents through two circuit elements in series are always the same. And just note how important it is that there are no junctions in between. If you have a junction in between, then the current that comes through A can get diverted. And so now you can't guarantee that the current through B is the same as the current through A, because there could be some going out through this junction, or there could be some coming in through this junction. The other way that circuit elements can be connected together, which is a special case, is in parallel. So here again I have two resistors, but they could be a resistor in a battery, or a resistor in a capacitor, or just anything. So here are two circuit elements. And we say they are in parallel if both ends of one are connected to both ends of the other, and the only thing in between them, in other words, if you walk from one to the other by either of the available paths, the only things you will pass are junctions. You won't pass any other circuit elements. If those two things are true, then we say that A and B here are in parallel. And again, this is important because of how this plays out for one of Kirchhoff's laws. Think about a loop. And if you walk around, starting below A here, up through A, and back through B, the potential you arrive back at must be the same as what you started at. And so the potentials, or the voltages across A and B, the differences in potential, must be equal. And again, note that it's important that there are only junctions in between them. If you insert another circuit element down here, and now think about this loop, you now can't guarantee that these two voltages are the same. All you can guarantee is that these three voltages all add up to 0. Now, it's important to realize that series and parallel are special cases. It's quite possible for circuit elements to be neither in series nor in parallel with each other. One really important thing to realize about circuits is that changing any circuit element tends to change what's going on everywhere else in the circuit. So for example, here's a simple circuit, fairly simple, with 3 resistors that I've called R1, R2, R3. And so they have currents through them that we might as well call I1, I2, I3. And let's think about what happens if we increase the resistance R3. Well, we'd expect that increasing that resistance is going to decrease this current. But there's a junction here, and so changing this current will tend to change this current because the sum of currents in and out here has to remain 0. So this current will probably change, but the current here is proportional to the voltage across this resistor. And so changing this current will change this voltage. Oh, but R2 and R3 are in parallel. So changing the voltage across R2 also changes the voltage across R3. And this loop has to have a total delta V around it of 0. So changing the voltage across R2 is also going to change the voltage across R1. So changing this one resistance, R3, has changed the currents through every resistor and the voltages across every resistor. Let's now look at how Kirchhoff's laws and our terminology of series and parallel helps us think about measuring things. So let's start with measuring voltage. A thing that we use for measuring voltage is just called a voltmeter, and the symbol for it is just this circle with a V. And let's think about how we would measure the voltage across this blue circuit element. Well, we want to make sure that the voltmeter has the same voltage across it as this does. That's how it's going to measure that voltage, by putting that voltage across it. Well, we know how to do that. If we put it in parallel with this, then they're guaranteed to have the same voltage across them. So that's always how we connect voltmeters, in parallel with the thing we're measuring the voltage across. But now here's the problem. There was a current running through this. If we connect up the voltmeter like this, now current can be diverted around this circuit element. And if this is a resistor or something similar, that's going to change the voltage across it. So we want to make sure that this current through the voltmeter is very, very small. Otherwise, it's going to change the value of the voltage we're actually measuring. So what we do is we make sure that the voltmeter has a large resistance, and a typical resistance for a voltmeter is about 20 mega ohms, which raises an issue. If you're going to measure the voltage across an object that has a large resistance, you may have to use a non-standard voltmeter that has a higher resistance, because your voltmeter must have a higher resistance, much higher than the thing that you're measuring the voltage across. Well, now we can have a nearly identical discussion for how we measure current. An instrument that we use for measuring a current is called an ammeter, and the symbol is just a circle with an A in it. And again, let's think about how we measure the current through this blue circuit element. So there's some current running through it, and we want to know what that is. Well, again, we want the same current to run through the circuit element and the ammeter. And we know how to do that. We need to connect the ammeter in series to be guaranteed that the current through the ammeter is the same as the thing that we're measuring the current through. Well, that means we're going to have to break the circuit here and connect the ammeter in this way. So that's an important thing to realize about ammeters. To properly measure a current basically always involves breaking the circuit so that you can insert the meter into it, unlike a voltmeter where you can just clip it on either side. Now, again, this brings up the same issue that I brought up with the voltmeter. Putting the ammeter in here could change what the current is through this branch of the circuit. And the way we make sure it doesn't is that we make sure that the ammeter has a very, very small resistance. And they vary quite a bit, but they're typically down in the range of milliohms.